So let's give a check at the speaker. Nicolita is here. Giulio is here. Paolo Fogliata is here.
Yes. Good morning.
Perfect. Good afternoon, Paolo. Lorenzo Berni. Lorenzo.
Yes. Yes.
Okay, great. And then Rodan Zhuang.
Yes, yes.
Great, great. So, perfect. Claudio, you can have the afternoon.
We start already.
Sorry?
Shall we start?
Yes, yes, absolutely.
Oh,
I will stop my voice.
So good afternoon, everybody, and welcome back to the meeting. We shall start immediately, not to lose time. We have a few speakers, 5 if I'm right. The first one is an invited, so you shall have 15 minutes. You all know the rules by the time, but just a brief reminder, 15 minutes for the first speaker invited, and then 10 minutes for all the others. And the auditors can post their question on the question and answer sections. And the speakers are invited to check the section and eventually reply the question during the meeting. The questions that will be left at the end, we will try to answer them directly. But of course, the more the meeting is interactive, the best it is. I think that's it for the time being. So, Michal, you have the floor. You can share your screen and start the presentation.
Okay, can you tell me that you see my presentation?
Yes.
Okay, so I will start to talk to you about the abandoned reservoirs and gully erosion analysis using LiDAR data. It is a work which it was presented in a paper, and it will appear in several papers. So we were a bigger team, but I will present today the idea of using LiDAR data, but also structure from motion technology to analyze these type of processes. Because I don't know how many of you know exactly the technology of LiDAR. We speak about laser beams that can be single or multiple returns. They can be mounted on planes, on drones, but they also can be terrestrial. So with this type of equipment, you can obtain point clouds. You can also see data under vegetation. So that they are very good in depicting real Earth topography compared with other interpolation technique. So in our case, having such a LiDAR data set, which was acquired using a plane. So we speak about the regional data set covering northeastern Romania with a very good density, 1 to 6 points per square meter. We were able to identify features that we knew that exist from the literature. In the last 500 years in northeastern Romania, a lot of small reservoirs were built, small and shallow. Their construction was required by the dryness of the climate, because they were used as mainly as cereal and fueler mills, but also later for pisciculture and also for water storage. The idea is that because the area is quite dry, so the discharge is not so big, after their filling, the morphology was kept and became smooth over the time. Later, sometimes they were, the dams, the reservoir dams were cut in the spillway area or in the central part of the dam in order to allow the water to flow, because these bottoms were used as pastures mainly, but sometimes also as arable land. So starting from that location where the water is concentrating upstream, very often gullies appeared. So this was our target. The reservoir mapping, it's quite straightforward. It's relatively hard to imagine automatic method because we have new dams, we have very old dams. You see here representations of this kind of dams. Some of them are quite new, some of them are quite old, some of them have mostly disappeared. We only see the sediments above them. So sometimes it's very difficult to have a decisive criterion, morphological one to map them. For example, here we have a reconstruction of the initial dam height using contours and using the extension of the sediments, of the filling sediments. We managed to create a regional inventory. We have sent for publication just a part of this inventory. And we were also able to create a temporal inventory using old maps and remote sensing data. Further on, we have observed the reservoir bottom gullies. We identified almost 600 sites where this phenomenon appear. Basically, for almost 500 of them, we were able to delineate them in a semi-automatical manner to estimate the volumes and also to establish a chronology. We have found that gully magnitude depends basically on the reservoir size, it's logical, and also on the location in the catchment, because the discharge at the high flows is the one that generates these gullies. So if we have bigger reservoirs on very on high order Strahler valleys, we will have big gullies, small gullies on smaller reservoirs on very small catchments. Also, the shape is very strange sometimes, because basically we have various types of tributaries. Not always we have a main channel creating them. So they can be dendritic, they can be ramificated, they can be very round or very rectangular. The methodology was based on using 3D views of shading, also using slope and the edge detection of slope. The edge detection of slope gave us the, let's say, the border of the gully, but we had to manually intervene because there are very strange situations when the gully is very close to the hill slope, so you do not have an edge and so on. So even if it seems a very easy task for a semi-automatical or automatical approach, actually it's quite difficult. You have here some examples of delineation. We also were able to interpolate the initial surface of the reservoir bottom. So we were able also to derive the volume of the gully. Here you have a plot of the depth versus volume of the gully. We have, let's say, a good correlation. But as I told you, the different shapes impose some departures from this general model, some outliers. The total volume that was eroded by these gullies is almost 700,000 cubic meters. But there is a huge variation between very small gullies to very long and big in volume gullies. As I told you, we also were able to establish chronology, which is mainly related to the climate of the area. Basically, in the 50s, in the 60s, there was a very dry period. After the 60s, in the 70s to the 90s, a very wet period. After that, we have again another dry period, but with very high flows, for example. For some of them, we were able also to see recent dynamics, and I will show you the part where we have used structure from motion and LiDAR data to establish the dynamics of the gullies. But we also were able to establish evolution model. We have reservoirs which are not gullied, but they are dried. They have a flat, relatively flat bottom, and they were cut in the central area. Sometimes people are creating straight drainage ditches in order to drain the area to use it as a pasture. Sometimes the river, there is enough discharge for the river to evolve to create a natural sinuous channel, or we can have gullies. As I told you, for some of them, we were able to use structure from motion, which was acquired in 2019. And we were able to determine the geomorphic change detection between 2012, the point in time when the LiDAR data was acquired, to 2019. We have flights in the beginning of the year, when the vegetation, so in winter, when the vegetation is not so well developed. Although in the area, we had to apply a geomorphological mapping approach beside the classical geomorphic change detection approach, which was discussed here and in other papers, because there are some differences between the LiDAR data, which was acquired also in February, but with some dry vegetation and with some snow cover, and the structure from motion data, which was acquired also in February, but without snow, and luckily with very small height of the vegetation. So we were able to target 4 gullies, which are very well developed in this, which evolved in this period between 2012 and 2019. So we were able to obtain very good geomorphic change detection data, which show us the extension of the gully in the main, let's say, part, also on the lateral parts. We also have been able to show deposition in gully fans downstream the gully for this specific gully. Also, for the geomorphological mapping, we have used the orthophoto imagery at under 1 centimeter resolution in order to obtain a very precise geomorphological mapping. There is also landsliding appearing in the gully heads, which is quite interesting. So we see a retreat of the gully head, of the principal gully head. We see erosion along the main channel. We see deposition along the main channel and above downstream the gully. You also have here some pictures which are showing the features. So they were checked in the field. This is the second gully, which only shows very high activity in the main head area, with a lot of landsliding, bank failure actually, which is related to probably to the springtime. This is a quite interesting gully which has evolved a lot along the main gully head. Here we see an interesting feature related to the LiDAR data, because in 2012, in February, there was snow and there was higher dry vegetation. You really need just 10 centimeters, and then you have to apply a specific methodology to remove that influence. That's why we had to apply a geomorphological mapping, basically, in order to constrict the geomorphic change detection approach. And this was successful. We were able to pinpoint exactly the landslide locations, the bank failures, the bank slumps, also some anthropic intervention, and the normal gully evolution through erosion of the banks and through deposition. This is the fourth gully, which is showing almost on all the heads evolution, retreat. Again, the dry vegetation was present, and the geomorphological mapping allowed us to basically pinpoint exactly the erosion and deposition areas. Here you have the volumes and the area which was attributed to the methodological error. Here you have the geomorphological mapping, and we were able to pinpoint exactly the volumes for every type of geomorphological process that was mapped. So in conclusion, these new remote sensing data and technologies like LiDAR and drones, photogrammetry, allow us to create inventories of specific landforms and to monitor this, the geomorphological process that affect these landforms. And basically, by coupling LiDAR data, which might be available at the regional scale, with drone surveys, we can monitor in detail this landform evolution. And this information has to be passed to the stakeholders and to the public. That's why we publish it, in order to be used for practical aspects. If you want to see weekly landslide and the gully from the Romania, check the Facebook page and my Twitter account. Thank you very much.
Thank you very much. Perfect timing. So very good presentation. I remind everybody that questions should be posted on question and answers, and we reply during the other presentation or at the end. And we go directly to the next presentation by Giulio Castelli. Giulio, if you are there, you can take the floor and share your screen. You have 10 minutes.
Okay. Thank you very much. Hope you can hear me correctly. And I'm just starting my...
Everything is working. You can go on.
Okay. Thank you very much for hosting this very interesting webinar. I think it's really a great venue, and I want to talk especially Paolo Tarolli, the University of Padova, for organizing. So my presentation is called Remote Sensing Advances in Agricultural Hydraulics and Watershed Protection, and is basically a contribution from the Agri department of the University of Florence, which deals with a series of applications in the sector of agricultural hydraulics and watershed protection. As some of you may know, our association, AIIA, and also the Italian university system is divided in sectors. And the sector of agricultural hydraulics is one of, let's say, the most interdisciplinary, dealing with a high number of topics connected to land and water management, including agricultural hydraulics, soil hydrology, irrigation, soil and water conservation, water management in general. So from here, we raise this question. So how remote sensing can help? Of course, it is a tool, but it's a very useful tool, even though it's not only born for the topic of agricultural water management. So first of all, it's very useful for expanding the scale from field site experiment to larger scale analysis. It allows us the extension of experiment in time, because remote sensing dataset have a very strong continuity, but also remote sensing can provide innovative kind of data and advanced information that we can use in sound land and water planning and management. I'm presenting a few case studies that came from our research experience. I hope to give a quick overview on what it can be done and what can be done apart from, very classical application like irrigation management and soil moisture study. So you see here, this is the first study we did in Tunisia about the study of the effect of water harvesting and soil conservation systems in arid and data scarce areas. Here, the local farmers crop olive trees, but also date palm in the so-called Jessur water harvesting system. It's a very remote area with a lot of smallholder farmers. It's very difficult to get soil moisture data and to have a proper assessment of the effectiveness of these measures. So what did we do with colleagues from the Institute of Arid Regions, which is an institute of the Ministry of Agriculture of Tunisia? We realized a soil moisture analysis at plot scale, but then with this soil moisture analysis, we realized calibration, and we retrieve soil moisture through the normalized different infrared index, which is quite well correlated to root zone soil moisture in arid condition, and we did it in Google Earth Engine. So thanks to this analysis, we were able to create longer time series analysis, which really confirmed that this kind of water harvesting system, which are very traditional, can increase soil moisture in dry season. Another typical example that we can consider as quite an advanced application of remote sensing is the estimation of vegetation roughness of riverine floodplains. Such theme, so the floodplains management is quite an issue because it can involve an high cost, but of course, if you cut down the vegetation in floodplains area, you may have some trade-offs. So if you keep the vegetation, you have an increased environmental quality, habitat and biodiversity, but you can have an increased flood hazard if you keep the vegetation in place. So you need quick, cost-effective, context-specific way of estimating modeling parameters for an hydrological modeling or an hydraulic modeling that can tell you if you have to cut or if you don't have to cut. So what has been done in another study with remote sensing is to use spot 5 image bands to analyze the correlation between the principal spectral components and some mechanic vegetation parameter, which can be used for estimating the hydraulic roughness that we have in riverine floodplains. And just to mention that this kind of analysis came from an older research that nowadays is very common in forest management, that is the estimation of vegetation parameters from LIDAR data. This is not particularly innovative, but it's nice to mention that also came from some application in our sector precisely for the estimation of roughness. Another interesting application that we study recently, again with Google Earth Engine, is to use the remote sensing of snow for analyzing how the spring snow melting in alpine catchments may contribute a lot with to the spring runoff that we observe at different altitudes. Basically, the catchment that are at higher altitude, they have a huge amount of runoff in spring that is generated by the snow melting. And this is another interesting application that we can consider by using such very quick tools of satellite image calculation like Google Earth Engine. This is another interesting application that is quite innovative, made by a colleague which did his PhD in our department. And of course, it's another way of using remote sensing, but it's not remote sensing in the air, it's remote sensing in the water. So in LAMA consortium, which basically is a section of the National Council of Research that we have in Tuscany, they are testing this new approach for the estimation of lakes and reservoirs volume. Basically, what we did is to drive, or better say, sail a drone, an aquatic drone in the reservoir, and then using a sonar for estimating the depth of the lake or reservoir in some points. This is very interesting because it's a very low-cost application. Actually, the sonar that is used is a fisherman tool, so it's quite cost-effective. Basically, is the sonar that fishermen use for checking the depth of rivers when they go fishing. And finally, this is probably the most advanced application that we use in our study. We have the microclimate analysis. So basically, by remote sensing, we could check not only soil moisture, but also other climatic variables, such like temperature. So we made the first study flying with a drone on a vineyard in order to analyze if there were thermal differences between grape rows which were internal or external in a terrace vineyard. So you see here, you have clearly the terrace represented, and you have the grapes. So what we found basically is that the internal rows in the morning are much colder than the external rows, but then in the afternoon, all the temperatures raise at the same level. This kind of element is very important because it can show how temperature can also be influenced by the geomorphology. And finally, another mesoclimate study analysis is the one that we made in Ethiopia. So basically here we calculate the water conservation index and the temperature index. And by satellite, we apply a time series analysis to a catchment where water harvesting was recently implemented. What we find out is that after the water harvesting implementation, which basically retain more water in the soil, we have a general increase in soil moisture while we had a lowering of the temperatures. And this is somehow expected. This is the so-called soil moisture temperature coupling. We have more water in the soil. We have more water available for evaporation. So what happens is that you deplete soil moisture by latent heat, you don't have sensible heat increase, and you have a decrease in average temperatures.
Sorry, your time is over. You should.
Yes, just quickly, I'm finishing. What do we expect? We expect a general increase on the power of calculation, and also new tools like the high atmosphere pseudo satellites. And we think that considering all this innovation, the use of remote sensing in our sector can be even stronger in next years. Sorry for this half minute late, and these are some references.
It's no problem. Just thank you. It was my duty to remind you that time is over. Very good then, just a very short delay, so we can quickly go to Paolo Fogliata. Paolo, I hope you are there and you can take the floor and share your
Thank
screen.
you. Okay, I share my presentation. Okay.
Okay, it's okay.
It's okay, perfect.
Yeah, we can see it.
Perfect. Okay, it's a pleasure to be here. This presentation is titled Analysis of Time Series Satellite Images as a Tool for Planning River Management Strategies. With this work, we want to present a simple methodology that studies the past river forms and helps to organize the future river management. So, as we know, river environment is a complex system. There are several ecosystem services that a river provides, and this can affect and improve the quality of the environment and our human life. In order to benefit of their services, the functions of the river must be maintained. And these are essentially the hydraulic function, which can be related to the hydraulic security, that can be especially in critical areas, for example, along infrastructure or buildings. Then the ecological function, so the morphological and the natural condition of the river, and then the landscaping function. All of this can be summarized as the hydromorphological functionality, which is a key point in the management perspective. Well, the most important natural components that we can find are water, sediments, and vegetation. These elements are directly involved in the regular management made by the technical agencies in Italy, and they are interconnected with each other. This because the management choices regarding a single part can affect the other and the entire environment. So the goal of the river maintenance is to find a balance among hydraulic security, river morphology, and environmental quality, trying to keep the ecosystem services effective. Well, in this way, remote sensing can be a useful decision-making instrument. And in particular, understanding the past hydrological and morphological forms is a crucial aspect for proper management plans. And time series satellite images are valid data to detect the fluvial forms, the sediment transport, and the dynamics of vegetation. Well, the main goal of this work is find a methodology that allows us to automatically classify the elements of water, sediments, and vegetation through a series of satellite images. Thanks to this, we will analyze the past river forms and study the variation over the years so as to organize proper management plans. Well, the methodology that we have built is articulated as follows. First, we got satellite images with different resolutions and covering a period of different years. For every year, we decided to apply the random forest, which is a common machine learning algorithm for classification. This algorithm is based on the information present on the single pixel, and it is also a supervised analysis. So before the application, it is necessary to create test areas to indicate to the system how to group the categories that we want to accomplish. Then, thanks to this, it was possible to extract the areas of water, vegetation, and sediments. Well, analyzing the performance of the random forest, for every image, we calculated the contingency table for having an indication of possible problems. Then on the area of vegetation, we also made a segmentation of the image. This new analysis is an unsupervised analysis, and it is based on the information present in the groups of the pixels. The results, so, will be an image with many fragments that needs to be grouped. And we assembled the various fragments by calculating the mean value of the NDVI for each of them. Thanks to this, we obtained a distinction between young and mature vegetation. So the area we have chosen as study area is the Oglio River, which is situated in northern Italy. And within it, we have selected two specific semi-natural section of the river, which a large presence of sediment bars, so as to understand their evolutions. Well, about the automatic classification for this first area, we come up with good outcomes. The macro areas of water, sediments, and vegetation are well defined, and the segmentation made on the basis on the NDVI shows a good distinction in the expansion of the foliage that can be a discriminant of the tree ages. Also, for the second area, we have obtained proper results, and especially for high resolution images. The only limitation that we have seen concerns low resolution images, and here, especially in the border of the elements where the size of the pixel can cover many different elements. And also here in low resolution images, the NDVI values may not be enough to divide the maturity stages for the same reason of the size of the pixel. Well, for about the river management, a practical example can be the evolution of the sediment islands and bar, and analyzing the variation of the extracted areas that we have calculated, we can define the sediment and the vegetation dynamics. In this first area, we have found that within the first 9 years, so from 2003 to 2012, the pioneer species expand and occupy a great part of the empty spaces. And then the vegetation started to stabilize the sediment bars, keeping constant the change in morphology of the river section. We can also see the same trend in the second study area. Here from 2003 to 2010, the vegetation expands, but it is also possible to see the drastic reduction of the vegetation after 2010. And this is caused by a clear cut that have changed the sediment stability and moved the bar to the other side of the river. Well, based on this evolution trend, we can define a threshold line for the expansion of the vegetation, above which it can necessary to take actions for its removal, and this in particular in critical areas such as near infrastructure and buildings. Especially here, the stabilization of islands can modify the path of the water, and it could go to erode the sensitive part of the river. Therefore, if every 5 years or so, or repeated technical agency carry out this type of analysis, they could obtain an indication of on which sediment island it is necessary to intervene and in what stage of evolution they are, so as to understand the future management timing. Well, as a conclusion, we can say that remote sensing analysis is an important tool from which it is possible to define river management planning, and in particular, understanding which areas it is good to intervene and in what times. For high resolution images, our methodology is able to detect the elements of the river environment, but in low resolution images, the NDVI values sometimes may not be enough to divide the maturity stages of vegetation. And other techniques, for example, the leaf area index or adding information with LiDAR data can be useful as a support. For a future direction, it is possible to carry out this methodology in other study area. Now we have, with this study, analyzed only semi-natural section of the river, but even in highly urbanized areas, or maybe where has been made a strong environmental restoration, can be really useful to understand the process of the river, and so planning the proper management operations. So this is all, and thank you for your attention.
Thank you very much, Paolo. Almost perfect timing, and so we quickly shift to the next presentation. Lorenzo Verni should be the presenter. I hope, Lorenzo, you're there. I can see you. Okay.
Yes.
Lorenzo, the floor is yours.
Thank you.
You can share the screen and start.
Okay. Can you see my screen?
Yeah.
Yeah, okay. My presentation is about this work, the possibility to have an early recognition of irrigated areas using Sentinel-2 data in central Italy. And so briefly, the main objective were to compare the effectiveness of different vegetation indexes from Sentinel-2 data, and also to compare different classification algorithms. And the classification was done both at the end of season when all the information is available, and also during the irrigation season to attempt an early classification of irrigated areas. And the database is represented by 92 areas in central Italy observed for the period 2017-2019 with known information about the crop type, and the presence of irrigation was simply defined according to the crop type. The main irrigation season is between May and September, which is a period characterized by a typical imbalance between evapotranspiration and precipitation. Here there is a list of some well-known vegetation indexes that were retrieved from both Sentinel-2A and 2B imagery for the same period, and were computed for with an average frequency of 5 days during the period May-September. Some details about the classification algorithms. We used the dynamic time warping and the random forest. Dynamic time warping is not strictly a classification algorithm. It is more a technique that is used for the comparison of different time series that can differ also for length and speed. So the technique has some advantages in comparison, for example, to the traditional Euclidean distance. And in the specific case of we use this technique for classification purposes. So yeah, there are some steps that were applied to obtain a classification from this type of technique. So first of all, we applied the daily interpolation of vegetation indexes during the time series, during the irrigation season. In this figure, you can see just an example for one of the index that were used, but just for 2 areas, but the same was done for all the areas and for all the indexes. After this daily interpolation, we quantified a mean dynamics for each vegetation index under the conditions of irrigated, for the condition of irrigated areas, and we fitted a double logistic function. So this figure show for this particular index the series that represents the reference series for the comparison of all the other dynamics. And according to the comparisons between this reference series and all the other series, it was possible to apply the dynamic time warping alignment and quantify the normalized distance. So simply, if the normalized distance was higher than a selected threshold, the area was considered non-irrigated, and otherwise it was considered irrigated. The threshold was defined simply maximizing the overall accuracy of the classification technique. The same approach was also used to obtain an early classification of irrigated areas, starting from the beginning of the irrigation season. And for this purpose, the reference series was compared, gradually increasing by a 15-day time step the length of each series to be tested. So more or less the approach is the same, but in this case, the overall accuracy can be computed as a function of the time from the beginning of the irrigation season. Random forest is a well-known classification algorithm. It consists in the creation of multiple independent decision trees. It is necessary to select a certain number of features. In this case, the features were 25 for each series of vegetation index. The features were represented by 25 values of the vegetation index during the irrigation season. And by applying, again, also in this case, the random forest algorithm, it was possible to quantify the overall accuracy of the classification technique in this case. As for the dynamic time warping, also the random forest was applied to obtain also an early evaluation of the accuracy. And so in this case, the number of features was gradually increased and to obtain an evaluation in time of the overall accuracy starting from the beginning of the irrigation season. The results, here there are the summary results related to the overall classification. So when all the information related to the dynamics of the vegetation index is available at the end of the season. Dynamic time warping and random forest are similar in terms of overall accuracy. There is a slight better performance of random forest. Among the indexes, NDVI and the modified SAVI2, which are both based on the near infrared and the red reflectance, are slightly better than NDMI. Instead, for the with regards to the comparison related to the early classification, in these figures you can see the progressive increase of the overall accuracy of the classification during the irrigation season as the number of features or as the number of information about the vegetation index increase. By dynamic time warping, we obtained a 90% of accuracy at about the mid of August, while instead by random forest, the same level of high accuracy, 90%, was obtained well before, about at the mid of July. So we tried to explore in more detail the reason of this difference, despite very similar performances at the end of the season. Of course, there are common problems in the use of vegetation indexes to identify irrigated areas, because it is necessary to have a certain growth of the crop, a certain vigor of the crop. However, in this specific case of random forest, it is also possible to explore the importance of the features of the different variables. In practice, in this case, it is the importance of the dates at which the vegetation indexes are observed. And if we look at this graph, we can see that, as expected, when the end of season classification is performed, the information related to the indexes observed in August is very, very important. And this is expected because in our climatic conditions, August is very critical in relation to the availability of water. Instead, for example, September is not so important for classification. But if we look at the similar results related to a early classification, in this case, the example refers to a classification performed at the end of July, we can see that it is strange that we can find some variables, for example, related to the end of May or to the beginning of June that are considered very important for the distinction between not irrigated and irrigated areas. In practice, we carried out a more detailed analysis, and we found that in this case, in this period, really random forest is able to perform a distinction between, a correct distinction between irrigated and not irrigated crops, because actually the mean values of vegetation indexes for irrigated crops is really lower than the same value for irrigated, not irrigated crops. So the classification is correct. Random forest is able to perform this distinction, and so to outperform dynamic time warping.
Yes, sorry, you should go to the conclusion.
Okay, I'm going to the conclusion. But really, the basic principle is something wrong. So in the main conclusions summarize the main results of this analysis that is still in progress. And I want just to point out that we are also working to consider the possibility to use the Sentinel-1 data, and the first results seems very promising. Thank you for your attention.
Thank you, Lorenzo. Just a very short delay, a very good presentation, and quickly to the next one. I should check the name because this is more difficult. Rudan Zhuang or Zhuang?
Yeah, yes, Rudan Zhuang.
Rudan Zhuang. So it's up to you, Rudan. You have the floor. You can share the screen.
Yeah.
I can see your presentation, so you can start.
Okay, thank you. Hello, everyone. Thanks for listening. I'm Rudan Zhuang, a PhD student in University of Basilicata, and also thanks to co-authors from University of Naples, Federico II. In this research, soil moisture retrievals from UAS systems, we are also working with the group members of Harmonious Working Group 3. Harmonious is a cost action on the use of UAS for environmental monitoring. Working Group 3 is focusing on soil moisture monitoring. Following, I will introduce the study area and the data, methods, and some results. The study area is a Montefort Cilento set located in Alento River Basin in Campania region. It's a typical cropland area called MFC2 of about 8 hectares. In MFC2, long-term studies on vadosome hydrology have been conducted across a range of spatial scales, include a wireless sensor network SoilNet with long-term 15 and 30 centimeter depth soil moisture observation, a cosmic ray probe available from 2016. The location of them can be found in Figure B, and several TDR measurements at each SoilNet probe's location were also conducted, especially the dates of UAS surveys, such as in October 2018 and June 2019. Usually in a UAS survey, we acquire one multispectral data set at the midday to reduce the shadow effect. 2 thermal data sets, one conducted before sunrise.
Volevo affacciare, anche perché io, tra l'altro, ti volevo chiedere.
Qualcuno ha il microfono acceso, dovete chiudere i microfoni, per favore.
Sorry. At midday and Two thermal data sets, one conducted before sunrise and one in the afternoon to obtain the most significant temperature difference. The RGB data were acquired along with the others. After processing using the structure from motion photogrammetric technique, the calibration we generated a digital surface model, 3 reflectance maps of red, green, and near-infrared bands, and also 2 land surface temperature maps. To generate high-resolution soil moisture, 3 methods were recommended. Thermal initial method is a reliable way to obtain soil moisture over bare soil and low vegetated area. Random forest regression model provide a possibility to downscale coarse resolution satellite-based soil moisture product with help of several land surface features. The simplified triangle model can provide not only soil moisture over vegetated area, but also the evapotranspiration. First, the thermal initial method. The soil temperature variations of one day can be generated from UAS thermal map, and from the multispectral image, NDVI can be obtained to extract bare soil pixels, and albedo can be used to calculate the apparent thermal inertia. After several post-processing procedures of RT, a regression model can be constructed with help of point-scale in-situ measured soil moisture, which can be further helped to generate the soil moisture map. Here we have one case in October 2018, which was published by Harmonious members in University of Palermo. The regression model was generated between TDR measurement, which obtained simultaneously with the UAS survey and the apparent thermal inertia in the same location in the map in Figure A. And the final map in Figure B is the estimation of the soil moisture distribution of the day. Here is a parallel case in June 2019. Compared with the previous case in October, it's under a relatively dry condition. We can find the difference parameters in the regression model. It could be interesting to have several parallel surveys and method applications. It may provide some hints to find the possibility to stabilize the parameters in the regression model and further to extend the applicability of one model. The second method here is a random forest regression model downscaling. The random forest regression model provides a possibility to link the land surface features and soil moisture statistically. As the available satellite-based soil moisture data are usually in a very coarse resolution, like 25 kilometers or 1 kilometers. And US-based land surface features, in this case, in very high resolution of 16 centimeters. We try to downscale 1 kilometer data directly to 16 centimeters. Some scale issues of land surface features were observed. So we proposed a 2-step downscaling with the help of land surface features in 30-meter resolution as intermediate data. The coarse resolution data used here include 1 kilometer soil moisture product from Sentinel-1, 1 kilometer land surface temperature and NDVI from MODIS, and 30-meter thermal band red and green band data from Landsat 8, and also DEM data from NASA SRTM. The first model was trained with 5 years 1 kilometer soil moisture data and land surface features, include rainfall, land surface temperature, NDVI, and DEM. The test result of the model is quite satisfactory as in Figure A, and we found rainfall and land surface temperature show a high importance in the model. And one applied the model with 30 meters corresponding land surface features, the estimation of soil moisture time series is acceptable as in Figure B. The dark blue line is the cosmic ray measured soil moisture, and the cyan line is the pixel value of estimated soil moisture. The second model was trained with the estimated 30-meter surface soil moisture and land surface features. Then the model was applied with the UAS data of June 2019. Except for the LST, NDVI, and DM, the topographic index and slope from DM are considered as features with better capability to describe the small-scale soil moisture distribution. We can see a preliminary results in Figure B and C. The last method is a simplified triangle model. The example case over one set in Palermo is also a publication by Harmonious members. In Figure B and C are the estimated soil moisture map and the validation results. Thanks a lot for listening. And here are some our Harmonious group members. Any questions are welcomed. And some related publications if you like.
Thank you very much. Thank you very much. We even recovered the short delay, so very good presentation. We can start with the question and answers. There are a few, so I will start reading some of them. There is one for Paolo Fogliata. Which satellite images did you use? Which classification, supervised, unsupervised, and which software?
Yes, okay, thank you. We had two sources for the images. First was the Planetech agency, where we bought high resolution images, and I'm talking about 1 meter resolution images, and that was non-free images. But the second source was planet.com, which is an agency that for research purpose gives freely images, satellite images with 3 meters resolutions. And these are opens and everyone can obtain it. About the about the Planetech, that was from Spot satellite, and the Planet sources have their own satellites. About the methodology, we did first an supervised analysis, which is the random forest, and we use QGIS plugins doing so. And about the segmentation, that was a non-supervised analysis, and we use a little Python script from that, but I'm trying to keep simple the analysis, so not using programming languages. I am confident to say that there are also other plugins for that, even from QGIS, and for example, even the Snap software from the European agency, that is also an open source software.
Okay, thank you, Paolo. This answers also to another question by Desalène Vorko-Ayalev, who was asking about data sources, in particular with reference to Ethiopia and countries where it is difficult to find data sources. But I think you replied already largely to this question. And there is one more for you. How can you identify pioneer vegetation and mature vegetation. So how can you discriminate between the two types? Which
yes, yes, good point. We use a threshold of the NDVI values. We calculated the values of NDVI for every period of the years, both from areas that we have identified as mature forest and areas that are pioneer species and young vegetation. We have seen that values about 0.5 and 0.7 can be a threshold. Below that, we can have pioneer vegetation, and above that, mature forest. And this probably is for the expansion of the coverage of the trees. But I want to underline that the NDVI method can be okay only for high resolution images, and I am referred to at least 3 meter per pixel resolution images, because below that a pixel can occupy even non-vegetated areas. So this is an important discrimination for me.
Okay. I've many for you, Paolo. Probably the other speaker, they already answered to some of them. I have one more for you, let's say, then I leave you in peace. Do you think your methodology can also be applied to flow resistance prediction in vegetated reclamation channels covered by rigid emergent riparian vegetation? So basically, do you think it could be applied to flow estimation?
Well, this is not so easy, because this methodology can can extract the areas of the elements, so the vegetation and bars, and with that it is possible to create a sort of models that predict the variation of the areas among years. So I think that understanding and predicting the how can I say, the flow resistance is with this model is probably not enough, so it is necessary to add some information, building a proper model for the evolution over the years and a correlation between flow resistance and presence of different kinds of vegetation.
Thank you, Paolo. One question for Rodan. Very interesting results for the random forest model. It seems model 1 performs quite satisfactorily, while model 2 a bit compromised. Do you also compare the one-step results with the two-step results at 16 centimeters? I hope you can understand the question. I would be difficult for me to answer.
Yeah, thanks a lot for the question. When we use the same features, so the same group of land surface features, the two-step result is slightly better, refers to like the correlation coefficient. And the reason why it's a bit like a compromised, first, we are still like exploring what is the best combination of land surface features at this scale from 30 meters to 16 centimeters. Second, and the training set we are using now, it's like the estimated 30 meters soil moisture. The frequency of it is based on the Landsat data frequency. So actually it's like a 16 days, every 16 days we have one data. So like it refers to like a 5 years data, then it's the training data number is much less than the like 1 kilometers data. So that's also the point. Like we can expand the training region or some other ways to improve the number of the training set. It may help the final results. Thanks.
Okay, there is a question which I can't even understand to whom is directed, but I put the question on the floor and maybe someone can answer it. How can we study biodiversity degradation in forest with remote sensing and knowing the species kinds and detecting the kind of species from satellite without going in the study area? So it's a very difficult question, but maybe, so basically understanding biodiversity and detecting different kinds of species from satellite. Is it feasible for remote areas without going there? Anyone has suggestions for this?
Well, we should always go in the field, or someone should go in the field, make a model, and only after that we can use only remote sensing images. So it's not feasible.
I have maybe, I think we still have a couple of minutes, and I would have maybe a question for Mihai. After listening to the presentation this morning and the afternoon, definitely one has the impression that remote sensing has a lot of potential. It has already a lot of application and more potential. But the thing is that there is a flood of information and of data that come in. And my question is related to the fact that we are hosted by an engineering association. So does this flood of information start finding a possibility to be used by, for example, by agencies, by public bodies, by consultants and engineers? So I remember I was back many years ago in a meeting in a congress in Budapest about filling the gap between theory and practice. I have the impression that this potential is huge, but we have somehow a duty to find a way to put it to the ground and find ways to exploit it completely in the applications. Do you think there is a sensibility to these issues and the capacity to take advantage of these, for example, by public bodies or consultants?
It really depends on the country. For example, in Romania, even we present these to the authorities, it's very difficult for them to take some measures or to use them sometimes, because this is the law in Romania. It's very difficult, but in other countries maybe. And since we publish them, I think everyone now has access to the papers and can even get the data and use it to create models. So the best idea is to share the results. And then, especially at European level, it's very easy to get the data to move around and to make studies. Unfortunately, in Romania, with the authorities, it's very difficult.
I was asking this question because, of course, the meeting was very, very successful. But maybe it could be an idea to, I don't know who the auditors, where did they come from, but I have the impression that most of us are coming from the academia or from research institutions. And it might be a good point for the next year or the next occasion to try and involve some people also from the public agencies and the practical applications, because I think that would be very interesting for them and very good for us to have the feedback. So this is my impression and maybe my message since Paolo, I don't know, but I think we are right in time for the closure.
Yes. Thank you, Claudio. Thank you so much. Before closing this successful day, I would like to ask to the panelists to open their video, their camera, so we can have a print screen of all the panelists, of all the speakers. In the morning, we had a large number of people that were following us. We reached more than 270. And now we are 166. It's good. I saw that some people just entered and went out just for some specific talk. So probably the cumulative number of attendees is larger because we had more than 800 people that registered. So fantastic to see your face. In order to close this great day, I just play a little bit with the Word Cloud software. I would like to share a kind of summary based on the keywords of the titles of the talks we had today. Just give a minute in order to see just the meeting looking at the cloud of Word. It's interesting to note that the main keyword is agricultural, but also we have data. So agricultural and data are the two main keywords, but also satellite, remote, LiDAR, comparison, evapotranspiration, drought. Mountains is a little bit smaller than the others, but this is interesting because we can see here maybe a future development in this kind of field because maybe drought, agriculture, evapotranspiration, and comparison and ecosystem. So I'm not sure, but looking also at the papers, the new trends also that we are observing recently in our sector, yes, I could like to, this is a confirmation that the next challenge of this century is agriculture and especially drought and water scarcity. And of course, remote sensing can play really an interesting role in this. So thank you so much. I will make available 4 videos. I will divide the videos by panel available in YouTube. So give me more days to play a little bit, to edit a little bit, because it is a large file to manage. Thank you for the invited speaker. Thank you for the moderator. Thank you to the Italian Society of Agricultural Engineering. And I hope to see you again, maybe in 2021 with another interesting webinar, maybe online. Doesn't matter if we will have still problem with the virus or not, but I think this is a good opportunity to make science and communication more inclusive, and reach a very, very big number of people, students around the world. See you in 2021. Thank you so much, and I wish you and your family the best.
Thank you.
Thank you.
Thank you, Paolo.
Thanks.
And
thank you, Paolo.
Thanks.
Thank you, Paolo.
Thank you.
Bye, everybody.
Bye, bye.
Bye, bye.
Bye-bye.
Bye.
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 Bye. Thank you.
Thank you.